I'm Grafton Conger.
And I'm Nathan Vincent, and today we're going to be talking about our fidget spinner CFD analysis.
So the first thing we'll be talking about is the fundamentals of CFD, also known as computational fluid dynamics. Computational fluid dynamics can predict the flow of a fluid around different objects, such as cars, wind turbines, or in the case of study today, we'll be looking at fidget spinners. The process of using CFD starts with creating the geometry or mesh to be able to define your object, define the process conditions like the flow, pressure, turbulence, and velocities, and then to run the simulation using different animations and pressure and velocity contours. There are a lot of other options for those vectors and contours, as I mentioned, which we'll get into a little bit as well. Next, we'll talk about the applications. So CFD can be used to aid in the prevention of cavitation on boat propellers. It can help with simulating rotating machinery, so like wind turbines, fidget spinners like we'll be doing today, as well as pump propellers to help prevent that cavitation and study the flow of fluid around it like air, water, or just different liquids in general. It can also simulate laminar and turbulent flow, which can be very useful in determining the cavitation, but it's not just used for cavitation. It can be used in studying many different applications, like aerodynamics in vehicles, planes, cars, and buildings, which one of the things that I really thought when I was doing research for this project was interesting was somebody built like an entire city of buildings in 3D and looked at the airflow through these buildings, which I thought was pretty cool. Heat transfer and battery simulation is another useful feature of CFD because you can look at the heat transfer through batteries and the flow of electricity through those batteries. And another interesting feature I thought was medical studies, because you can use CFD to study the flow of blood and different fluids throughout the body, which I thought was a really cool aspect. And I had never really thought of being able to use CFD in medical until I started doing this project. So benefits of CFD: it can be cheaper than creating a real model. It can also be faster than using a real model, because whenever you're having to use a full physical model, you have to first build it, then you have to design it, and then from there you can't make changes as easily, and you also have to do the hand calculations for it. So like say you want to change like the length of a wing on a plane model that you made, well, you have to basically rebuild the entire wing in order to change that length. And then after you do that, you have to redo all those hand calculations, while CFD does all of this for you frame by frame. And makes, like I was mentioning, it makes those changes much easier and makes engineering more flexible in changing the design as well as the different conditions that the object may be in. It can also give you more detailed analysis because it's doing these animations and pressure and velocity and just different temperature contours and things like that frame by frame. It can also help with the design of different components in a variety of industries, such as the car industry, determining lift and drag on cars and the flow of air around those different vehicles, as well as in buildings, as I mentioned earlier. And then hopefully for this study to help determine between which fidget spinner is better, whether it be a 2-blade fidget spinner or a 3-blade fidget spinner, which is what we're going to get into now. So just to kind of make a fun CFD project, me and Nathan decided to go ahead and look at the two different fidget spinners, whether it be a 2-blade or 3-blade, on which one actually is better. And through this, we'll be looking at the turbulence, the pressure, and velocity contours of these fidget spinners to determine which design is better. Here's the SOLIDWORKS model that we based our design off of. We found this drawing online and decided, this is probably like a good base model to base it off of. The dimensions are in millimeters, and we drew this model in 2D to run the simulation. Some of the difficulties for making this for the 3-blade model was we first had to play with it to kind of figure it out, because trying to draw it all at once didn't work, like drawing different rectangles. When we tried to angle it, it said it was overdimensioned. So what we did instead was drew 3 lines, angled it, and then drew rectangles off of those lines in order to get the correct shape. And the circle in the middle is 0.035 meters, and the smaller circles are on the edges are 0.03 meters. And then we connected the circles with rectangles because they were already at the right angles. So here's another important feature. once you draw your fidget spinner, both for 2D and 3D, which you'll see, we'll show you the 2D pictures, or the not 2D, the 2-blade and 3-blade fidget spinners. Well, once you get to your 2-blade fidget spinner, it's the exact same process, which we'll explain in a little bit, and we'll show you the pictures. But once you get this far, you have to draw a circle around your fidget spinner in the same sketch, and make it a 0.3 meter diameter. This is very important because you want to be able to make your fidget spinner able to rotate whenever we get to the animation stage. And then once you do this, you'll create your surface by sketch and do a boolean. You'll do the surface by sketch on your fidget spinner first, and then you'll do a surface by sketch on the circle, and do a boolean and subtract the fidget spinner from the circle in order to separate the two features. Next, you want to do a new sketch on the same plane to make your airfoil. This arc here will have a 1 meter radius. The horizontal length of the rectangle, which you can't really see in the slide, but there's a rectangle connected to this arc going to the right, will have a 1 meter length or width, I guess, and then a 2 meter height to cover the whole diameter of the circle. And then to finish it off, you'll want to draw a circle over the same circle that you drew for your rotating circle for the fidget spinner. And then you'll do a concept and surface by sketches to make that surface there. For the meshing, you'll name the left side of your airfoil the inlet, the right side of the airfoil the outlet, and then you want to name your fidget spinner as well, and then also the two different circles as interface in and interface out for your rotating, and then your circle on the airfoil. For the meshing, though, we would do a triangle meshing instead of a quadrilateral because you want it to be, for round surfaces, you generally want to use triangles just to get a more accurate meshing. And then for the rotating circle, which is the circle that we drew around the fidget spinner, not the one for the airfoil, we did a body sizing and made the element size 0.02 and did a hard mesh. And then for the airfoil circle, we did the same thing. We did a 0.02 element size for a body sizing and then made it hard as well. For the fidget spinner, we did an edge sizing, selected all of the edges, and then it did a 0.01 meter and also made that a hard meshing. And then for the general mesh sizing, which isn't selected on anything, it's just you click mesh in the command window and change the element size to 0.5 meters. Once you've done all of this, you want to do a refinement of 2 to shrink your meshing in order to get a finer mesh around your fidget spinner. Because that's what we're focusing on for this study. So for the setup, we did a transient setup because it's not going to be under steady flow conditions. We did a K epsilon model just to get a more accurate model for turbulent flow, and did enhanced wall treatment in order to make it a smoother transition between the two models. We made the material air because that's what fidget spinners generally are flowing in, and then did a cell zone condition to have 44.82 radians per second, which is really important because that's the average angular velocity for a fidget spinner from what we found online. And then change the boundary conditions to have an inlet velocity of 0.9 meters per second, which is the x direction velocity, because that's the speed of ambient air from our research. You want to make sure to change it to a magnitude and direction condition, and then also change it to an intensity and length scale. And then for the fidget spinner boundary conditions, we want to make it a moving wall as well as rotational. For the solution methods, we changed them all to second order and did a hybrid initialization. And then wanted to do animations for velocity and pressure. Once we had that, we wanted to run our calculations at 800 time steps at 0.005 for the time step size to get a more accurate time step, and then to do a max iteration of 40 iterations.
Alright, so now we're going to go into the two-wing model and how we got that all set up. So it's going to be very similar, in fact, pretty much exactly the same as the three-wing model. The only difference is the geometry of it. So in the makings of it, we have 2 wings, not 3, and the difference being the wings are separated by 180 degrees here versus in the 3-wing they're 120 degrees. You'll note here that we'll use the same Boolean subtraction for this meshing, or for this geometry and meshing, we will have the same 0.3 meters circle that surrounds the fidget spinner itself, and that's all for the two-wing model. So now we're going to hop into the velocity contours. This is the three-wing velocity contour. Here you can see the slow, this is the blue here is the slower velocity, and that represents drag. And the bigger the blue blob is, the more drag that we have. And on the bottom side there, you can see red, which is just faster airflow over the wings there. And I want you keeping this in mind when we compare it to the two-wing. So compared to the two-wing here, our velocity is the blue blob is actually much smaller, meaning that we would have a less drag at this moment in the picture. And on the bottom, you also see there's the same red high-speed air flowing over the bottom of the two-wing there. And here is the pressure of the three-wing. We have a bit of red on top there that represents a higher pressure, and on the back side you see a little bit of blue, that's a lower pressure. I want you to keep that in mind when we go look at the two-wing. So on the two-wing here we can see that we have a very well distributed higher pressure on the left side of the two-wing compared to the three-wing. This may hint that the two-wing's not going to do as well because there's a lot more force or a lot more pressure hitting on it, so it may slow down faster than the three-wing. And here is the turbulence of the three-wing. The turbulence of the three-wing here, you can see the red bit is the higher points of turbulence, the blue is the lowest point of turbulence. There's very little red there up on the front of the top left of the three-wing fidget spinner, and if you follow back you can see a trail of turbulence, and you see the green blob. There's also a little bit of turbulence way in the back right corner. Now looking at the two-wing turbulence, we see this red arc wrapping around the top. That shows a high concentration of turbulence flowing and arcing over the two-wing, meaning that we have way more turbulence in the two-wing versus the three-wing, and this also still has the same giant green blob on the back and on the right there.
So some of the conclusions that we can make from these contours is when you look at that velocity contour between the three-wing and the two-wing, though the three-wing has a little bit more drag coming off the back, that slower velocity where it kind of turns into a big blue balloon almost on those two velocity contours, shows that it's encountering some form of drag there. But so that's one consideration that we took into it. But it did have higher velocities around the total fidget spinner itself than the two-wing. And then when you look at the pressure on the between the three-wing and the three-wing had a lot less pressure acting against it as compared to the two-wing, where it had a pretty evenly distributed amount of pressure acting against the two-wing. And then when you get to that turbulence, it's definitely the two-wing has a lot more turbulence than the three-wing does. So just based off of those results that we've had in our study, it kind of hints towards having the three-wing fidget spinner would last longer with the spin time than the two-wing would, just based on the turbulence and the amount of velocity and pressure for each of these components.
So here we can see our velocity animations for the three-wing fidget spinner here. And you can see it remains pretty stable throughout the whole cycle as it rotates several times. On to the next one. We have the two-wing fidget spinner velocity animations. Very similar. It repeats. It's a pretty stable system here. And here are the pressure animations for the three-wing. And here is the pressure animations for the two-wing. Alright, so part of our project here, we went and looked into the differences between good meshing and bad meshing. So here we have an example of bad meshing that we actually tried out. And we used a quadrilateral meshing, which isn't favorable here. It'd actually be better to do a triangular meshing. So for the bad meshing, we did a quadrilateral meshing, and we had a 1 meter general size mesh applied, which resulted in much less nodes than a good mesh which you'd want in a good mesh. And there was no refinement done, so there's even less nodes because of that compared to our good meshing that you'll see on the next slide here.
Yeah, and also, as we mentioned earlier, on the earlier meshing, you generally want to use a triangle mesh for whenever you have round surfaces like we have on this fidget spinner as well as the airfoil to make it more concentrated. And then with the refinement, it also will help you make more concentrated meshing. Like it reduces the size of your meshes by a factor of 2 or 3, whichever refinement you try to do. And whenever we have the edge sizing around our fidget spinner, it'll make it focus more and more on that fidget spinner, which you'll see here in a second when Nathan shows you the difference between the velocity contour of the good mesh versus the velocity contour of the bad mesh.
All right, so here is the bad meshing results. You can see how the blue and the green there's a fuzzy point between it in which it's not very clear of what the velocity is, and that is part of the mesh being not as well made. You can also see this light blue ring or circle. There's a light blue circle that surrounds the fidget spinner there, and that's actually the 0.3 meter circle that we put in our geometry earlier that rotates, that gives the inference that our fidget spinner is rotating. Well, because our mesh isn't very fine right there, it actually changes and shows the velocity being different there, versus like having a better mesh. You'll see that like there won't be that visible blue circle around the fidget spinner. So here you can see there isn't like that well defined, like not so well defined, that line, that circular line around that's in blue. Here you can clearly see where our velocities are at and get a good idea of their speed based off the colors. And there isn't a whole lot of blending of colors here.
So in conclusion, just based off of what we saw with the velocity contours of the fidget spinner, the through-wing, like I mentioned earlier, encountered more drag. The pressure contour of the two wings showed that the fidget spinner encountered more resistance from the pressure, and then from the turbulence, it also had a significantly more amount of turbulence. And so that helped us to conclude that based off of our studies and 2D, the three-wing fidget spinner would ultimately last longer on its spin time. And then going back to between the fine versus the poor mesh, the fine mesh helped focus closer to the object of study and gives a more accurate result versus the poor mesh, which would extend the measured contours further away from the object of the study. As you can kind of see in those previous pictures from the bad mesh versus the good mesh contour velocity, it was more like a disturbed velocity. It wasn't as uniform as the fine mesh velocity contour was. So if you would like to continue the study, Nathan can kind of explain how we did a 3D model here.
So we went and made a model of the fidget spinner on SolidWorks, which we could then import over to ANSYS and run a CFD model on it. Now, we haven't yet run a CFD model. I just went and made this example here on SolidWorks, which we'll be having a crack at, and then we'll eventually compare the results between the 3D model and the 2D model, or the 3D model will show much more detail of how air is flowing over the fidget spinner versus the 2D, because everything in the world that we have is 3D, so you can only get so much out of the 2D models.
Yeah, so just due to the time constraints we had on the project at the time of completing it, we weren't able to ultimately solve how to do this 3D problem. We hope to work on it in the future. But if you'd like to just continue the study for fun and just see the difference between a 2D model and a 3D model, then that is something you will be able to work on. This model is based off the drawing that we did earlier in our results. and here are our references, and that is everything we have. Thank you for your time.